If you're joining on the live stream, it's just going to be 1 more minute there. Restarting the computer over in Marcus. So.
All right, sorry, there's still something wrong with the webcam. I'll just turn it off. All right.
Can you hear me okay, Ivan?
Yeah.
You're a little choppy on your side.
Oh, yeah, I can hear you.
Okay. So are we ready to roll?
Yep.
Awesome. All right. So hello, good morning, everybody. I hope you are having a nice week. As we know, we are headed into our last week before spring break. So we have a couple things to cover, and then there'll be 1 week off from classes, and then we'll come back. And so I just want to talk about sort of the Thursday class for a second, because it's split and it might be a little goofy on Moodle. So I just want to make sure you understand sort of what's happening. So today we're going to cover 3.2, and today's stuff is sort of the normal structure. There'll be the mini quiz on Wednesday. But then on Thursday, we're going to do the first half of what's called the chain rule. And the chain rule is probably one of the most complicated things we cover. So it's split into 2 lectures. So we're only going to do the first half on Thursday, which means that you do not have a mini quiz on Sunday. You just have the homework for the week from 3.2. Then when we get back from spring break, we'll do the other half of the chain rule, and then the quiz will be on Wednesday of the week after we get back. And so one of the things I want to sort of really strongly encourage you to do is to work on the chain rule homework that you can do after Thursday's lecture before spring break starts, because the homework is pretty complicated because of the process of the chain rule. And then you can finish the homework once we get back, but it is split, which is why you don't see a mini quiz due this Sunday. Okay, so last class we started talking about derivative formulas, and today we're going to continue that. Excuse me. So last time we talked about polynomial terms. So we had constants, we had mx, and we had x to the p, something like that. And then at the end, we added sine and cosine. Today, we're going to be talking about the derivative formulas for exponentials and natural logs. So we're going to be adding on to our list of derivative formulas that we will be using moving forward. So I'm going to go ahead and switch over to the doc cam. All right. So today we're going to be considering, again, formulas that have come from doing lots and lots of limits and approximations that mathematicians did a long time ago, and they noticed a pattern. And from that pattern, we were able to get a formula. And so just to sort of highlight where this formula comes from, if we were to consider the instantaneous rate of change at every single point for a function like 3 to the x. Okay, so 3 to the x is this black function right here. If you were to find the derivative at every single point and you were to graph it, you get something that ends up looking like this. And you can see that that is very, very similar. And you're like, that's really interesting. Those two things look a lot alike, right? So if you were to do this again with 2 to the x, right? Again, 2 to the x is an exponential function. And you were to graph the derivative at every single point, you get something that looks like this. And again, you may think, that's really interesting. Those look very similar. So if you were to graph 4 to the x, 5 to the x, 6 to the x, right, and keep doing all these exponential functions, then you find a pattern. right? And it's not super surprising, but what that pattern results in is a derivative that is also an exponential function, right? So we have an exponential function, and the derivative also ends up being an exponential function. But what we see is that they're not quite the same, right? So the derivative is not exactly the same as the exponential function. So there's some factor that is multiplying to get the derivative. So it turns out that when you do this process, the formula that results is that if f of x equals a to the x, then f prime of x equals a to the x times the natural log of the base, okay? So we get the same exact function back that we're starting with. And then we have this factor that we multiply. And the factor that we multiply is the natural log of whatever this base is down here in the bottom. So for example, you have f of x equals 2 to the x. That's the picture we looked at. The derivative is going to be the same thing back, 2 to the x, times the natural log of the base. But the base here is 2. So remember, the natural log of 2 is just a constant. Okay, so that's a number, and that multiplies our function. Now, there's a couple of rules that come along with this that are special cases that we want to talk about. Okay, so this is the general rule right here. And you can always use the general rule. Now, the first sort of special case of this is e to the x, okay? So e is a number, it's approximately 2.71. And so this is an exponential function, which means we can apply this rule. But what happens when we apply this rule is we get e to the x times the natural log of the base, right? But the natural log of e, if you remember from algebra, is 1, okay? And anything times 1 is itself. So that means that when you take the derivative of e to the x, you get back e to the x, right? You get the same thing back that you started with. And that's the only time it happens is if the base is e. And that's because when you apply this rule, this factor happens to be 1, okay? And then there's a spin-off of this rule for our third case that requires a little bit of algebra. So let's say we have a function that is e to the cx. So now we have some number up in the power, right? Could be 5, could be 10, but it's a constant. Now, I want you to remember from algebra that e to the cx is the same thing as e to the c to the x power, right? If you have a power raised to a power, you multiply them together. You can also separate them back out, which means that when we take the derivative of this function, we can treat this as the base, right? This is an exponential function with a number raised to the x. So when we take the derivative, we get the same thing back, e to the cx, times the natural log of the base. But in order for this formula to work, our base needs to be a single number, which here is e to the c. So natural log of e to the c. Now we know from our natural log rules that the c can come down in front and that the natural log of e is 1, which means that our derivative is e to the cx times c. So what does that look like, right? What's an example? So let's say we have f of x equals e to the 10x, right? So this only works if it's just a constant. What this special case says is that the derivative of this is the same thing back, e to the 10x, times the constant that's in the power. So times 10, okay? And so again, this is our general rule. the derivative of a to the x is a to the x times the natural log of a. This is a special case of this rule. So the derivative of e to the x is e to the x. And then this third one is an algebraic way of figuring out how to take the derivative of e to the cx using these two rules. So the derivative of e to the cx is e to the cx times c. So these are the rules we're going to be working with today. To start with, we'll add one more in a little bit, but just as a reminder, we had these rules from before. So these are from last time. Right? We had a constant, we had mx, and we had x to the p power. And now we're going to practice just adding on some of our basic exponentials. So that's a to the x, the derivative is a to the x, ln a, and e to the x. So the derivative is just e to the x, okay? So we're going to start by practicing these. We're going to try this for these 4 exponential functions to make sure we can apply these 2 rules correctly. So the first one is 7 to the x. The second one is e to the x. The third one is 1.2 to the x. And the last one is pi to the x. So think about how we can apply these 2 rules that we've added on. I'm going to give you 2 minutes to try it out, see if you can find those derivatives, and then we'll go through them together. Okay, take about 30 more seconds. All right, so let's try to apply our rules to these exponentials so we can get used to how these are going to work for us. So the first one, we have 7 to the x. So when we take the derivative of 7 to the x, our base here is 7. So we get the same thing back, 7 to the x, times the natural log of the base. Okay, so I just want to remind you, 7 to the x is a function. Natural log of 7 is a constant, right? So this has the x in it, this doesn't. So this is just a number, okay? So those are multiplied together to give us our derivative. For the next one, we have e to the x. So again, that's our special case, and the derivative of e to the x is just e to the x. So we just get the same thing back. For part C, we have 1.2 to the x. So the derivative is going to be the same thing back, 1.2 to the x, times the natural log of the base. So the base here is 1.2. So our derivative looks like this. And then for the last one, we have pi to the x. So we get back pi to the x times the natural log of the base, which is pi. So pi to the x times the natural log of pi. Now, I want to take a minute just as like an algebra reminder, because this you'll see may come up in some ways later today. If you have something like 3 times 4 to the x, right? So you have a constant times a function. You cannot combine the 3 and the 4 because this altogether is a function, just like we were talking about before, which means that you can't change the base of the function. These two things have to stay connected. You can't make this 12 to the x or 12 something like that. So when you have something that's in the power, your variable's up here in the power, you cannot change the base. Okay, so just keep that in mind. Okay, so now we've done some very sort of strategic, basic exponential functions. And I also want to take this time to remind you that when I use the word basic in this class, it doesn't mean easy, it means foundational. So I'm going to use the word basic a lot in chapter 3, and it does not mean easy because these are not easy, you know, until you practice them and you get really good at them. So I don't want you to think that when I say basic, that means you should understand everything right away. It means these are the foundational derivatives and formulas that we're going to build upon. Okay, so we're going to add the partner derivative here of the natural log of x. So we know that natural logs go with exponential functions. These are paired, right? Because these operate as reciprocal functions. So when we take the derivative of the natural log of x, and again, mathematicians just plotted out the derivative at every point and figured out what this function is, we get 1 over x. Okay, so the derivative of the natural log of x is 1 over x. As a reminder, if you have something like the natural log of 10, the derivative of the natural log of 10 is 0 because this is a constant. Okay, so one thing that trips people up a lot is they'll see something like just the natural log of 10 by itself, and then they'll try to say that the derivative is 1 over 10, which it's not, because you have to have that x in there for it to be a function, and it has to be the function before you can apply that derivative rule. Okay, so just try to keep that in mind as we sort of work through some of these problems. So we've updated our list now. I'm just adding in the natural log of x is 1 over x, okay? And so what we want to do is we want to think about how we might do these derivatives with the other properties we've talked about. We talked about the constant multiple rule. We've talked about sums and differences. So if you have terms that are added or subtracted, we can go term by term. And so we really want to practice those particular rules, right, in the context of these new derivative formulas we're learning, right? So the constant multiple rule says that if you have something multiplied in front of the function, that number will multiply the derivative of the function. The sums and differences says that if you add or subtract things, you can certainly take the derivative of each piece and add or subtract the derivatives. And then the second derivative process is also going to apply for the work that we're doing. So if you want to find the second derivative of a function, you're going to apply the formula twice. So we're going to start with the constant multiple rule and the sums and differences rule. And so I want you to practice this by trying to find the derivatives of these 4 functions, which include a mix of exponential and natural log functions. You'll see that there's a constant of 2 here. So we're going to apply the constant multiple rule. We have a 3 here, a 5 here. So think about that. And then again, use the sums and differences rule. So I'm going to give you 2 to 3 minutes to try out these 4 derivatives, see if you can sketch them out using the rules we've just talked about, and then we will go through them together. Okay, take about 30 more seconds. All right, so let's go through these. So for the first one here, our first term is 5 to the x. So this is just a standalone exponential function. So we'll just apply our rule that we get the same thing back times the natural log of the base for our first term. Then we have a minus, and then we have natural log of x. So we take the derivative of that from our chart. We get 1 over x. And then we have plus 2 times 3 to the x. So that 2 brings in our constant multiple rule, which means we're going to have 2 times the derivative of 3 to the x, which is 3 to the x times the natural log of the base. So our entire derivative looks like this. Again, going term by term and applying our different rules. Now, our second one, we start with e to the x. The derivative of e to the x is just e to the x. And now our second term has a 3 in front. So we're using our constant multiple rule, which means we're going to have 3 times the derivative of the natural log. The derivative of the natural log is 1 over x. So you can write it like this, or some people prefer to write the second term by bringing the 3 into the numerator. Oops, it should be e minus 3 over x. Okay, so 3 times 1 over x is the same as 3 over x. Either one is fine, it's just a matter of preference, but just know that if you see something written like this, that it means the same thing as this, right? So 3 times 1 over x is the same as 3 over x. For part C, we start with the 10 to the x term. So we get 10 to the x times the natural log of the base. So we get 10 to the x times the natural log of 10, plus, now here we have this 5, so we're using the constant multiple rule. So 5 times, and then the derivative of the natural log of x is 1 over x. So again, you can leave it as 5 times 1 over x, or you can write it as 5 over x. Those mean the same thing. And then for our last one here, we start with e to the x. The derivative of e to the x is e to the x. Then we have 6 to the x. So the derivative of 6 to the x, 6 to the x, natural log of 6, minus the derivative of ln x is 1 over x. Okay, so again, if things are separated by addition or subtraction, we go term by term, and if there's a constant in front, that constant multiplies the derivative of the function. Okay, so the next thing we want to practice is some second derivatives using our rules. And so this particular problem has a couple pieces here. So the original function is 2 to the x plus e to the x minus x to the 2/3. So that's one from last time. So we have to remember the power rule, minus ln x plus 6. And so what I want you to do is I want you to find the first derivative using our basic rules. And once you do that, I then want you to evaluate f prime of 1. So that means you're plugging a 1 into the derivative, and I'm asking you to give an exact answer. So what does that mean? That means you shouldn't turn anything into a decimal. So your answer might have like an e in it or a natural log. You don't want to turn anything into a decimal. We want to practice making sure we know how to present exact answers. Then you're going to find the second derivative. So you're going to use the first derivative and apply rules again to find the second derivative. Get that all written out. And then I want you to evaluate the second derivative at 1, getting an exact answer. So again, plugging a 1 into the second derivative. So I do want to give you a heads up that the second derivative is a little bit trickier than the first derivative. So if you can get the first derivative and the first derivative at 1, great. If the second derivative feels a little trickier, see if you can figure out the terms that you can find the second derivative of, and then we'll go from there. So I'm going to give you about 3 minutes to try this out, see how far you can get, see what you can figure out, and then we'll go through it together. Okay, take about 30 more seconds. All right, so let's go through these and make sure we have all the pieces and can think really carefully about plugging things in and second derivatives. So we're going to start with just the first derivative function. We notice here that there's a bunch of terms separated by addition and subtraction. So we can go term by term and evaluate the derivative of each term. So the first term we have here is 2 to the x. When we take the derivative of 2 to the x, we get 2 to the x times the natural log of the base. So times the natural log of 2. Okay. The next term, we have e to the x. The derivative of e to the x is e to the x. Our next term, we have a polynomial term. So we have to think about what we learned last class, and we see that x is in the base. So that means we're using the power rule. So that means the power is going to come down out front, and we're going to subtract 1 from the power. So we have 2/3 x. Now we're going to subtract 1 from the power. So 2/3 minus 1 is -1/3. The next term is the natural log of x, so minus 1/x. And then finally, we have a +6. So the 6 is by itself. It's a constant that's not attached to a function. So when we take the derivative will be 0 because that's a constant. So our first derivative as a function looks like this. Now, if we want to evaluate this at 1, this will give us the rate of change of this function at x equals 1. So the rate of change is the derivative, right? It's the slope of the tangent line. So we have to plug in a 1 everywhere we see an x, right? So we have 2 to the 1 times the natural log of 2 plus e to the 1 minus 2/3 times 1 to the -1/3 minus 1/1. So the question becomes, what can we simplify and what needs to stay sort of as it's presented? So here, the first term, we have 2 to the 1 times the natural log of 2. The natural log of 2 is an exact number. We don't want to turn that into a decimal. So we're going to leave this term sort of as is. Anything to the 1 power is just itself. So the way we would write the first term is 2 natural log of 2. Okay, we can't simplify that any more than that. E to the 1, same thing. So e is a function in itself, and when we plug in 1, it's a number, but it's an irrational number, and we don't want to turn it into a decimal because we want the exact answer. So e to the 1, we can just write as e because we don't usually write the 1 power. Now here, we have 1 to the -1/3 times -2/3. Okay, 1 to any power is just going to be 1. So 1 times -2/3 is -2/3. Okay, so this is the same thing as -2/3 instead of -2/3 times 1, And 1/1 is 1. So we can combine these two numbers to get a single constant by using fractions. So -2/3 minus 1 is going to be -5/3. So we can write -5/3. Okay, so this is how we would write an exact answer when we've plugged in 1. We didn't turn anything into decimals. We only really simplified by combining our constants, and then we were able to get the function that we want. So that's what that looks like. Okay, so now we're going to go to the second derivative. And so when we talk about the second derivative, we're going back to the first derivative, right, to the function. We don't want to do it here because these are all constants. And we need to take the derivative of each term. Now, I want to point out that in the first term, we have this natural log of 2. Okay, so that's a constant. So that means that we are going to be using the constant multiple rule. So I'm going to take that constant, the natural log of 2, and that constant has to multiply the derivative of 2 to the x. Okay, so the derivative of 2 to the x is 2 to the x times the natural log of 2. Okay, so what I really want to sort of point out here is that this natural log of 2, the first one, is the constant from before, and the second natural log of 2 is the result of taking the derivative of 2 to the x. Okay, because we can see now that there's 2 of them, and we'll talk about that in a few minutes, but that's how we get to the derivative of that first term. Now, the derivative of e to the x is just still e to the x. Now, for our next term, I have -2/3 x to the -1/3. So the -1/3 is going to come down and multiply the minus. So I'm going to end up with plus. And now the 1/3 times 2/3 is going to give me 2/9 x. And when I subtract 1 from the power, I end up with -4/3. So I have to be careful when subtracting here. And then the last term is a little bit tricky. So I want you to think about, we talked about this term, I think, maybe once in the last class, but 1/x has to be rewritten, right? We can't deal with an x in the denominator. This is the same thing as x to the -1 power. So now we started with a natural log derivative, but now we're using a power rule derivative to get to the second derivative. So we're taking the derivative of x to the -1, okay? So when the -1 comes down, it's going to cancel that minus, and we're going to get plus, right? And now here, we're going to have x to the -2 because we subtract 1 from the power, okay? So that part's a little tricky. So if you didn't quite get that, that's okay. That's why we're doing it together. And now again, we want to plug in a 1 into our second derivative to see what shakes out. So we start by just plugging in a 1 everywhere we see an x, just so we can start to think about how we want to simplify. So I'm just going through, and everywhere I see an x, I'm plugging in my 1. Okay. And now I need to think about, how do I simplify this but keep it exact? So for the first term, again, I see I have some natural logs in there. I don't want to turn those into decimals. And so I'm going to do a little rearranging because I have 3 things that are multiplied together. And so I'm going to pull the 2 to the 1 to the front. And now I have a natural log of 2 times a natural log of 2, which is the natural log of 2 squared, right? Just like 3 times 3 is 3 squared, natural log of 2 times natural log of 2 is natural log of 2 squared. Plus e to the 1, we can write as e. And then again, remember that 1 to any power is going to be 1. So this is 2/9 plus 1 to the -2 is 1. So I can combine these by finding a common denominator. So 2/9 plus 9/9 gives me plus 11/9. Okay, so this particular problem has a lot of terms in it that are irrational, and we want exact answers here. So this is how we could write an exact answer without turning anything into decimals. So that's our second derivative evaluated at 1. So again, we're just sort of practicing working with exponentials and natural logs in all the ways that we practiced with our power functions last class. So for our next example, we're going to do find the equation of the tangent line. Excuse me. So again, we had a whole process from last time. So I'll just quickly review the process, and then we'll see if we can apply it here. So in order to find the equation of a line, we have y equals mx plus b. So we need the slope and we need a point. We get the slope by finding the derivative and evaluating it at the point we're interested in. And we get our point by plugging in the point we're interested in into the original function. That gives us the shared point between the function and the tangent line. Then we assemble the equation of the line by using the slope and the point with y equals mx plus b. So I'm going to give you about 2 minutes. I want you to try this out, see what you can remember about this process from last class. Obviously, the function has changed. Now we have an exponential, but try it out, and then we will go through it together. Okay, take about 30 more seconds. All right. So again, we need a point and a slope. It doesn't matter which order we find these. So I'm going to go ahead and find the point first. So I want to plug a 0 into my function because that will give me the y value for my point. So I have 2 times e to the 0. As a reminder, anything to the 0 power is 1. So 2 times 1 is 2, which means when x equals 0, y equals 2. And so my shared point between the equation or between the tangent line and the function, it touches right at the point 0, 2. So that's my point. I also need my slope. I get my slope from the first derivative. So here, I'm going to take the first derivative of my function in general first. So here I see a constant multiple rule. So I have 2, and then the derivative of e to the x is e to the x. Once I have my general first derivative, I want to evaluate that at the point that I'm interested in, which is 0. So 2 times e to the 0. So again, that's going to give me 2, which means that my slope is 2. So now I have a slope and I have a point. So I'm going to put that together in y equals mx plus b. So I start with the m. So y equals 2x plus b. Now I'm going to take my point and plug it in. So when x is 0, y is 2. 2 times 0 is 0. So that tells me that b equals 2. So the final equation of my tangent line here is y equals 2x plus 2. Okay, so again, quick process. We find a point by plugging the value into the original function. We find the slope by finding the first derivative. Once we have the slope and the point, we assemble it using y equals mx plus b. As I mentioned, this is a very common problem that we'll look at throughout chapter 3, finding the equation of the tangent line, but with different types of functions. So to that extent, we're going to try one more with a natural log function. So find the equation of the tangent line to the function 3 natural log of x at x equals 1. Okay, so again, apply the same process. I'm going to give you about 2 minutes, find the point, find the slope, and assemble into y equals mx plus b. And so in 2 minutes, we will go through it together. Okay, take about 30 more seconds. All right, so let's see if we can put this all together. So again, we want to plug our x value into our function to get the corresponding y value. So we have 3 times the natural log of 1. Okay, so if you remember, the natural log of 1 is one of our special values that actually is a whole number. So if you were to plug that into the calculator, or maybe you remember, the natural log of 1 is 0. So 3 times 0 is 0. So we have x equals 1, y equals 0, which is the point 1 comma 0. Okay, so now we also need to get our slope. So we start by finding the derivative of this function. So the 3 is a constant multiple. The derivative of the natural log of x is 1 over x. So our general derivative looks like this, but we want to know what is happening at 1. So we have 3 times 1 over 1, which is 1. So 1 times 3 gives us a slope of 3. So now we have a slope and we have a point. We want to put them together. So we have y equals 3x plus b. Now we want to plug in our point. When x is 1, y is 0. So here we have 0 equals 3 plus b. We subtract 3 to the other side and we get b equals -3. So now putting it all together, we get y equals 3x minus 3, since b was -3. So we get the equation of our tangent line. So again, whenever we do this type of problem, the equation of the tangent line, the process is always the same. What's changing is the type of function that we're working with. So as we learn different derivative rules, we can try this with different types of functions. Okay, so now we're going to go to an example that is a bit longer. Okay, and so this one, we're going to kind of go piece by piece, because not only are we working through our derivative stuff, we are learning a new concept about a particular function that shows up in business quite a bit. Okay, so we're going to sort of go step by step and do it piece by piece so we can figure out how all of this fits together. So when money is invested, it gains value depending on a lot of different things, right? So how the market's doing, the global economy, what you've invested it in, all those sorts of things. One of the really important factors that comes in is how the money is compounded. So what that means is different types of accounts give you interest at different amounts of time. So some accounts give you interest once a year. Sometimes they give it to you once a month. Sometimes they give it to you daily, right? So it really depends on the account. So when we talk about compounding, that's how often the interest is added to what's called the principal amount. So the principal amount is the amount you invest to start with, okay? So if the interest is added once per year, we say that that's compounded annually, okay? And so the equation for annual compounding is given by FV equals PV times 1 plus R to the T. So FV represents future value. So how much money you're going to have at the end of this investment. PV is the present value, which is also the principal investment. And that's the amount you start with. R is the interest rate that you're going to get for your money. And we do that in decimal form. So if it's 4%, we do 0.04. And then time is T, and that is given in years. Okay, so if you leave your money in for 1 year, time will be 1. If you leave it in for 2 years, time will be 2. Okay, so part A, we just want to practice using this formula before we do anything fancy with it. So suppose you invest $1,000 in an account that has an interest rate of 2.5%. How much money will you have in that account in 5 years? So I want you to take a minute and a half, 2 minutes, right? Figure out how all these numbers get plugged into this formula based on what we just discussed, and see if you can figure out how much will be in the account in 5 years. So again, we're just getting used to this formula, so we're literally plugging directly into this formula to get started. So take a minute, try that out, see if you can figure that out. Okay, I think about 30 more seconds. Okay, so the way that we work with these numbers, we are looking for a future value because we want to know how much we'll have in 5 years. And we know that that's equal to the present value or the amount you start with. So that's the $1,000 times 1 plus R. So R is the interest rate. Here we're getting 2.5%, but we need to write that as a decimal. So 0.025, and that's raised to T, the number of years. Okay, so I want to point out the reason we have this 1 in the equation, because the 1 says you get to keep the $1,000 and then you add the interest to it. So the 1 is what keeps the amount there as part of this calculation. So then we put this in the calculator and we get $1,131.41. Okay, so if you're getting a 2.5 interest rate on your $1,000, after 5 years, you have $1,131.41. I want to point out that in this scenario and in the money problems we talk about, we sort of ignore the fact that you can lose money. So maybe this is like a savings account or something that's guaranteed. This is not like the stock market, right, where you can lose money. This is something like a bond or a savings account, something like that. Okay, so that's how we plug things into the general formula, right? You have the amount you start with, the interest rate, the time, you can figure out how much you'll have at the end. Now, again, this is assuming what we said was annual compounding, right? So this was 1 time per year. The bank or whoever goes in says you have $1,000, dump some interest in. Okay. Now, another way that we can compound money is monthly. And this is how most savings accounts work, is monthly. So this means that once a month, interest is added to your account. However, that does not mean that you receive the interest rate for the account each month. Instead, the interest rate is divided up by 12 for the calculation. So like if you're getting 12% on your account and you have monthly compounding, you get 1% each month to get a total of 12%. Hopefully that makes sense. So the formula for when we're going to compound monthly gets adapted to look like this. So future value equals present value, so the amount you start with, 1 plus R divided by 12. So we're dividing whatever our interest rate is into 12 different payments, right? Because we're getting it 12 times. So it's going to add up to R over the year. And then the number of times, right, is the year times 12, because it's happening 12 times each year. So that means that the amount of times we compound is 12 times T. So again, R gets divided by 12, and now the exponent becomes 12 times T. So assuming the same initial amount, so the $1,000, right, the same interest rate, so 0.025 was our interest rate before, and the same number of years as part A, so we're still talking about 5 years. Now I want you to calculate the future value again, but doing monthly compounding, right? So now we're going to do the same thing, but with this formula, because we're doing it monthly. Okay, and the question is, before you do this calculation, do you think that the final amount is going to be bigger or smaller than $1,131.41? So again, we're still only getting 2.5%, but it's divided up to get a little bit each month. So do you think that'll be more or less than doing it once per year? So make a guess whether you think it'll be bigger or smaller, and then go ahead and see if you can apply those numbers to our new compounding formula. I'll give you 2 minutes and then we'll go through it together. Okay, take about 30 more seconds. All right, so in the interest of space, I'm just going to write the work up here. So we're assuming that everything is the same as part A in terms of the numbers, but now we're compounding more frequently. So here I start with present value, which is still $1,000. I have a 1 plus, now R over 12. So what is my rate here? So remember, my rate is 0.025. So 0.025 divided by 12. And now I'm going to do 12 times 5 in the power, right? Because 60 different times, so 12 times 5 is 60, 60 different times over the 5 years, I'm going to get interest. And the rate that I get is the interest rate divided by 12. When I carefully plug that all into the calculator, I get $1,168.93. Okay, so I get more money than if I was compounding annually. Why would that be true? Because every time you compound, you get money on the interest that you have earned. So this first year, right? What am I going to get? $25, right? 1,000 times 1.025 the first year. So that means that the second year, when I get interest, it's on the $1,000 plus the interest that I got in the first year. So if I'm getting interest more often, that means I'm getting interest on my interest more often. Now, you may not think this is a huge difference, right? $1,131.41 and $1,168.93 over 5 years. But imagine that you're investing $10,000 or $100,000. All of a sudden, that difference adds up very quickly. So knowing how your money is compounded makes a difference. So if you had the opportunity to invest in something that, say, has a 4% interest rate that's compounded annually versus another way to invest 4% that's compounded monthly, same interest rate, so you may think it's the same, but now you know different. You know that if you compound monthly, you actually end up with more money in the end, okay? So now that we've sort of taken the time to understand the variables and what we're talking about in terms of money, now we can bring in this idea of rates of change, okay? So for part C, for each of the general formulas, so that's this one, PV 1 plus R to the T, and PV 1 plus R over 12 to the 12 times T, we want to come up with the rate at which the future value is changing. So we're trying to take the derivative of each of these functions, okay? And so you can see that we have a number in the base raised to the T. So these are exponential functions. We have to be really careful. The second one's a bit trickier than the first one. But how can we apply our exponential function formulas to these particular situational formulas? So for part C, we're trying to come up with the formulas. And then for part D, once we have the formulas, we want to go ahead and calculate the rate that each function is changing at time equals 3. So after 3 years, right, how much is this function changing? If the present value is 1,000, the interest rate is 0.025. So somewhere in the middle of this investment, we're trying to figure out how quickly the rate is changing, okay? So I'm going to give you 3 to 4 minutes. See if you can figure out how to find the derivative of each of these formulas. If you can successfully do that, you can go ahead and plug in these values, but try your best. Try to remember what is a constant and what is the variable here. And then think about our exponential function derivatives and how we can apply them, okay? So try it out, and then we will go through it together in a couple minutes. Okay, take about 30 more seconds. All right. So for the first one, we're starting with the formula FV equals PV times 1 plus R to the T. So again, we really need to make sure we understand what the variable is here versus what is a constant. So what is varying is time, right? So our independent variable here is time. And so that's up here in the power, which is why we know this is an exponential. Since the 1 plus R is what is raised to the T, that means that the 1 plus R is the base. So this is our base. And PV is a constant multiple. So it's a number in front that multiplies the function. So that means when we take the derivative, we get the constant multiple, PV back, times, now remember with exponentials, we're going to get the same thing back, 1 plus R to the T, times the natural log of the base. So the base here is the entire 1 plus R, right? Because it's in parentheses. So it's this whole thing that is raised to the T. So our derivative looks like this for that first function. Now for the second function I mentioned, this one's a little bit harder. So we have PV times 1 plus R over 12 raised to the 12T. So when we started class, we did the e to the cx example where we had some constant up in the power. And we said, okay, we need to algebraically rewrite this so it's just to the x power. So we're going to do the same thing here where we're going to rewrite it so we have something just to the t power. And the way we make this adjustment is by pulling out the base to the 12th power and then raising that whole thing to the t power. Because if you have a power raised to a power, you would multiply the powers together and you'd get back this original function. So by pulling out the base to the 12th power, we're able to raise it all to the single t power, because again, t is our variable. So the PV is again a constant multiple, so the amount you start with. So we get PV times, now when we take the derivative of an exponential function, we get the same thing back. So we have 1 plus r over 12 times 12 to the t times the natural log of the base. So this is why this separation is so important, because the base is this entire piece, including the 12, right? The base is whatever is not the power of t. So the natural log of 1 plus r over 12 to the 12 is the base. Okay, that one is tricky. There's a bit of algebra involved in the back end of it. So if you weren't able to get the derivative of the second one, hopefully now seeing it out, it makes sense. So remember, the natural log piece should be the natural log of some sort of constant. So here 1 plus r is a constant because r is a rate. Here 1 plus r over 12 to the 12th, that will be a number. So that's also a constant. The t only shows up in this part of the formula. So then for part D, once you have these formulas, we just want to plug in these values. Okay, so here for the first one, when we plug that in, we're going to get that the rate of change is 1,000, 1 plus 0.025. Now our t in this instance is 3, so to the 3 times the natural log of 1 plus 0.025. So once we carefully plug in all those numbers, we're going to put that into our calculator, because you're not going to do that in your head or anything. And we are going to get that that crunches to $26.59. Now let's talk about the units. So it's dollars per year. So remember that when we talk about units, it's the dependent units over the independent units. The dependent units are going to be in money because future value, we're talking about money, so dollars. The independent units are time, right? That's what we're varying, and that's per year. So that means that the investment account is increasing at a rate of $26.59 per year, given this interest rate and this time. Now, for the second one, again, we're just carefully plugging in all these numbers. So 1 plus 0.025 over 12, 12 times 3, because our t is 3 here, times the natural log of 1 plus 0.025 over 12 to the 12th. Right? So there's a lot of parentheses in this one. So you just have to be really, really careful when you're plugging this into your calculator. It's really easy to make mistakes. So much so that I'll say double check my work if you didn't get the same answer. I could definitely have made a mistake on my calculator. There's so many parentheses. But the rate of change for this one will be $26.92 per year. And we are expecting this one to be higher because we know compounding more often gives you more money. Okay, so that's the end of the class today with exponential type functions. Practice these on homework, and on Thursday we'll pick up with the chain rule, which is a little more advanced derivative techniques.